Log on, tune in, find out. Another good idea from Cambridge.
Loud enough. Sound on? Okay. Well, let me also thank the organizers for having me here. Actually, for a few weeks, has been a great time spending here with old friends and new people I've been working with never before. It's a great pleasure. What I would like to talk about is a few elements, a theoretical insight in the problem of full waveform inversion. So, full waveform inversion is a very old idea, and it has had a major revival over the past few years. And really what is interesting to see is sometimes you see it sort of converges in numerical experiments, sometimes it doesn't. And the question is, can we actually develop some theory to get some insight whether full waveform inversion can converge? And the idea is very simple. Go back to the analysis of inverse problems and try to bridge some of the analysis of inverse problems to iterative methods, whether you can actually have an iteration to converge to the true solution. Now necessarily that's going to be a local theory, as you know. I mean, you cannot with iterations do a global reconstruction, but how far can you actually go away from the true solution? What are the conditions, what are the rates of convergence that you can expect? And for that we go back to the Helmholtz equation. So we're going to do it in frequency. And really the whole idea is that the convergence we are going to tie to, well, the uniqueness theorem from the nonlinear inverse problems that I'm not going to talk about, and to a stability, a conditional stability estimate. That is sort of the gist of the story today. And again, I'll point a few theoretical techniques that give you an idea how you can glue that together. Now this is joint work with Elena Barretta, Lingbing Zhu, and Ottmar Scherzer in a couple of papers. And so why can we go back to the Helmholtz equation? Why is it popular again to do that? Well, there's a nice machinery for inverse theory, but also we can essentially afford to compute the solutions to the Helmholtz equations. In fact, we can afford to compute it for many right-hand sides, so many boundary values, by the development for a whole range of new direct solvers. We developed our own using hierarchically semi-separable matrix structures, a massively parallel algorithm together with Shen Wang, Jingling Xia, and Sherry Lee from Lawrence Berkeley Lab. We can do models of the order of 1,000 cube, 2,000 cube, factorized essentially, like an LU factorization. So you have the numerical tools that this becomes reality. It can really be done in a very reasonable time. And so that means we can actually look at the Dirichlet-Neumann map as the data, which we want to from an inverse problems point of view. So we're going essentially to look at fixed frequency, a variable speed, 1 over c squared, and we're going to map that to the Dirichlet-Neumann map, which I quickly will review. And once you do that, once you consider the Dirichlet-Neumann map as the frequency data, well, then necessarily you end up in Banach spaces. You have to work a little bit hard what you exactly mean by an iterative technique, and I'll give you a flavor of how that can be done as well to stay close to the inverse problems theory. Now, how do you get control over convergence? Well, you can do it probably many ways, but the way we addressed it is we're going to look at conditional Lipschitz stability or Hölder stability of this Dirichlet-Neumann map inverse problem. And well, then you say, well, when does that happen? I'll give you the conditions when that will happen. But then immediately say, well, what I would like to preserve in those conditions is a singularity structure. We want to allow essentially reflectors still to survive in such a kind of analysis, which you can, which brings you back to, well, a starting point of view that the speed should really be an L infinity function. Now that is sort of bad news because all those iteration techniques work in reflexive spaces, and so you have to maneuver a little bit around. Now the conditional stability brings you in another world, not an L infinity world, which helps you to actually address this issue that is sort of an open issue from a practical point of view. And so the stability will require some structure and dimension to the problem that I will be precise about. And this dimension will lead us to the notion that it is attractive to think in terms of compression. You want to have low-dimensional model representations to get stability. So it's conditional, and hence the technique that you expect will work, which we work out, is going to a projected iterative techniques, and the simplest category is the steepest descent, which has to be made nonlinear in this setting. Now, what I immediately need to highlight that the whole idea was really motivated by various papers, but in particular by the work of Alessandrini and Vesela on the electrical impedance tomography problem, where they worked out those stability estimates, which you can carry over to the Helmholtz problem with quite some work. And last but not least, we want to ensure that we can deal with partial boundary data, which again, inverse problems theory allows you to do that. So that is sort of the big picture. And so, of course, by no means I can go in all the details. We're going to highlight a few elements how you can, in principle, build such a theory. So this is the Dirichlet-Neumann map. So we translate the seismic problem into a boundary value problem. You have the Helmholtz equation. For now, 1 over c squared is L infinity. And we apply a boundary function, g, on the boundary. And then we measure the normal derivative, the trace of the normal derivative on the boundary. That's the Dirichlet-Neumann map, which is analytic in frequency, which we will not exploit here. And essentially then you design a forward map that goes as 1 over c squared for fixed frequency to the Dirichlet-Neumann map. And here you have to do manipulations in what sort of norm you're going to measure actually your convergence, because the reflexivity of the space in which you have to start. So you can think of L6 or do some other things. So F is a nonlinear operator-valued map. And so from now I'm going to simplify the notation. I'm going to talk about F, the Dirichlet-Neumann map will be Y, and Q, omega squared over c squared will be X. And so we're going for, make a little detour in how you can actually think about iterative techniques in spaces that are not the usual least squares, but the Banach spaces. Now there's a whole machinery out there in the literature. It's known as Bregman iterations, and I would like to just have a few slides how this, roughly speaking, works. So again, the Dirichlet-Neumann map lives in a Banach space, and let us assume that 1 over c squared lives in a Banach space as well. Dual spaces, we have to go and iterate, and we have to iterate in the right spaces. So think of it as an adjoint state method. You cannot stay in the Banach spaces, you have to do the iteration in the dual spaces, and eventually go back, which you don't have an inner product. So you start with the Banach spaces, the original model space in the data space, the duals, x star and y star, you have norms, and you have a duality product to connect it to, the standard function analysis setting. And so we are going to assume that x is reflexive. So we have an operator equation, and the operator equation is the Dirichlet-Neumann map problem. And I'm going to skip over the conditions when this problem is unique. The stability conditions immediately guarantee uniqueness of this problem. So we know that there is a solution that will reproduce the data. At least we're going to stay locally around that solution. So we have an attainability of the problem. And so the objective is find an iterative method to give continuous approximations to the inverse of this map. That would be full waveform inversion in its, perhaps in its ultimate form. And so how do you do that? Well, you have to work in dual spaces, and so to iterate you cannot stay in the usual norms of the Banach spaces. This again is known techniques in the geometry of Banach spaces. And let us just highlight a few things. First, we need some notion of duality mappings, and in preparation thereof we actually need to have the notion of convexity and smoothness. So you introduce a convexity modulus, delta x, which is defined at the top, and you introduce a smoothness modulus rho. Now, we need the constants, and that is why I'm just writing this out. P convexity is described by an estimate in terms of the convexity modulus over here. So that is estimated in epsilon to the power p, and Q smoothness is estimated into a polynomial estimate in terms of tau in the power q. So essentially, those are the constants that play a role later on in the estimates. My point is, I want to highlight where certain constants play a role, because those constants eventually play a role how we are going to play with multi-frequency, the well-practiced frequency continuation. How are you actually going to exploit it? And for that you need to know where all the constants appear. So how do we iterate? So again, to iterate we need duality mappings. So duality mappings are J. They essentially go from the Banach space to its dual, and in general it maps onto subsets. It is not single valued. So JP is one of those duality mappings defined over here via the duality product, which is here computed with a gauge function, and the gauge function is essentially the mapping T to T in the power P minus 1, which is right on the right. Now we are going to invoke some conditions to make JP single valued. And how do you do that? By assuming that X is uniformly smooth. Well, if you have Q smoothness, P convexity, then that is all guaranteed. So we have a JP. Now think of JP as sort of what you need once you really start to do like the analog of an adjoint state calculation. So if it is uniformly convex, the duality mapping is actually bijective, but we don't need that. So you get the duality mapping going back from x star to x. P and Q are in the usual duality related. 1/p plus 1/q is 1 throughout the whole talk, the whole analysis. Now the typical example are the LP or LR spaces, where the duality is basically LR and LS, where 1/r plus 1/s equals 1. So this is sort of the general space framework in which you can think. And so we are not, due to the duality mappings, we are not going to iterate in minimizing a norm. We're going to iterate, and that is known as the Brakman iteration, minimize in the so-called Brakman distance. Now just for completeness, I give you what it is. It is a particular way of measuring distance between two solutions. It is not a metric, and it is because it doesn't satisfy the triangle inequality. But other than that, it has all the convergence properties that you want. So if you have a sequence that converges then in norm, then actually it converges in Brakman distance and in the dual sense as well. So for all the purpose of convergence of iterative techniques, this is a perfectly fine tool, even though it doesn't satisfy, again, the triangle inequality. And so two constants now play a role that will reappear soon. We assume that x is p convex, and that gives us an estimate for the Brakman distance of this type. This constant Cp will appear, and then the dual will be q smooth. Those two imply one another, and the constant of that estimate is gq. So p smoothness and q convexity and their constant estimates play a role in how actually this all works. So just a picture, if you have never seen the Brakman distance, this is sort of a cartoon how it works. So you have a Banach space X, the dual X star. Think of the duality mapping as this graph. Then this is the Banach space norm in X. Over there is the Banach space norm in the dual. And what the Brakman distance does, it measures sort of the distance across from the tangent. And so this is actually in a sense how we measure the distance. That is how the Brakman iteration should be thought of. And so here comes the iteration scheme, prior to saying anything about convergence. This is a Landweber iteration. And the Landweber iteration you take as an objective functional, as I write here. So you take, in this case, the p power of fx minus y, and you iterate, and the iteration is over here. So it goes by duality argument. So here's your residual. You apply the duality mapping. This is your Fréchet derivative that you apply the adjoint, the dual, not the adjoint, the dual to. Then, well, this is the previous, from the previous step, and mu is the step size. So it looks just like a standard Landweber iteration, except it is nonlinear. And so this is how you compute the dual to the next step. And to find the next step is you have to apply the dual back to the original, the dual to the dual, back to the original space. So it's essentially a two-step iteration. But think of this as replacing your standard adjoint state if you follow a Landweber iteration approach. And so again, Jp is the duality mapping from x to x star. Q star brings you back. And small jp, which is over here, does the duality mapping on the data side, on the side where the Dirichlet-Neumann map lives. So that is roughly speaking how the machinery works. And so now we come to the key statements, the convergence analysis. First of all, you can prove that the Dirichlet-Neumann map, as it is in terms of operator, is Lipschitz continuous, and its Fréchet derivative is Lipschitz continuous. So those conditions that I write down above are actually satisfied in the setting that I described. The constants L and L hat, in particular L hat, the Lipschitz, the bound on the Fréchet derivative, plays a role in the convergence estimate. So L hat is the next constant to keep track of. This constant is going to be frequency dependent due to the frequency in the Helmholtz operator. F is supposed to be weakly sequentially closed in our setting that is satisfied as well. So this condition in the Dirichlet-Neumann map case is satisfied as well. And now we come in the key condition, that is the condition of stability. We do it slightly more general than Lipschitz. We assume for now that, well, in the Brakman distance, the problem is Lipschitz stable. So we can estimate the distance between two solutions in terms of the distance between the Dirichlet-Neumann maps corresponding with those solutions, where epsilon equals 0 corresponds with Hölder a half, and epsilon equals 1, the other bound is precisely Lipschitz. Asymptotically, Sometimes you can get Hölder estimates, so that is why you don't only want to do Lipschitz if you go back and study in detail the Dirichlet-Neumann map. Now we're going to study this problem around in the vicinity of the unique solution in sort of the analog of a ball of radius rho, and rho will be the basin of attraction. So this will give you guarantee if you have an estimate for rho, within rho it will actually converge to the true solution. So what I haven't said yet is that you can attain this stability, and I'll come to that in one slide ahead. But here comes the story. So if those conditions are satisfied, if your step size satisfies some technical conditions, so here you see L hat appearing, and you see CF. CF is the Lipschitz stability constant appearing, and they change dramatically depending on what models or what frequency you use. You have to satisfy those two inequalities, which look technical, but you can find explicit examples. So you can actually come up with sequences of step sizes where those conditions are satisfied. Then everything converges within the following convergence radius away from the true solution. That is given by, well, a bunch of constants. Here are those constants that I mentioned before. Let us put them aside. What you see that L hat, the Lipschitz constant and the bound and the Fauché derivative, and the stability constant play a role. So what you immediately see, for example, is that if the stability constant becomes bad, becomes large, this is a negative power, if epsilon equals 1, then actually the radius of convergence contracts very rapidly. And so the stability is extremely important to guarantee that you have any sort of non-trivial range where you can attract to the true solution guaranteed. So the interplay of the constant is the interesting part here. Then once you have convergence, you can estimate convergence rate. So if you have Lipschitz stability, which we can attain, then you have linear convergence. This is as fast as it can get in iterative techniques. If you have Hölder regularity less than Lipschitz, but greater or equal than a half, you have sublinear convergence, so the convergence is slower. And you can compute all the constants in terms of all those estimates in closed form. So again, all those constants of stability, of the Lipschitz constant, and of the inverse problems Lipschitz stability constant appear in the right powers. So you have essentially complete control of what happens. So now comes the question, can you ever get there? And so this statement is a generalization of the case of the electrical impedance tomography case. It was motivated by it. It required a new proof. So essentially the statement is the following. We can get Lipschitz stability for the Helmholtz equation, starting from an L infinity point of view, if the following is true. If the 1 over c squared, keep omega fixed, omega can be complex for that matter. If it is true that I can expand 1 over c squared in a finite linear combination of piecewise constant functions, where, well, there are some constraints on the shapes of the domains. You need certain Lipschitz regularity of the shapes of the domains. And what you need is what I don't write down, a technical condition that if I have partial boundary data, there's a precise condition on the connectivity. So if you want to reconstruct the functions on domains in the interior, they need to connect in a particular way to the boundary where you actually have data available. So it's a partial result. Then it is true that you have Lipschitz stability, which you can translate into a Brakman distance result. And so this is the statement. And so here's that Lipschitz stability constant. So you can do it on domains, you can do it on simplices. Essentially what the conditions means, I cannot have simplices where corners become arbitrarily thin. So you need some sort of conditions that it is sort of a reasonably well-behaved mesh. So then the stability condition holds. Now that is the good news, because that means that in principle, conditionally, the Landweber iteration will converge. I get control over the problem. The bad news is what you can also prove, and again it is a technical argument, a topological argument, that CF grows exponentially with the number of domains. So mind you that the radius of convergence collapses when CF grows. So if the number of domains grow, then exponentially the radius of convergence will contract. So then you say, well, what do you do? Well, what I need is I need to work with a small number of domains. So I need sparsity, and I need to be able to control the shapes of the domains. So shape optimization becomes very important. But in principle, you can do this. So now the story is, how do you mitigate this growth? So of course the real world is not piecewise constant, even though probably many of your codes assume that. 10 minutes, good. And so the story is, well, if the real world is not that, I can have singularities. That is sort of the key point, that you have piecewise constant functions. So I need to come up with an approximation theory. So what you say, well, what I really should do is you should say, well, I have a true model that is complicated, that I'm going to approximate by compression by those sort of functions. And so we're going to place those functions into convex sets, and we're going to translate this whole story by doing approximate versions of what we just did to find the minimum Bregman distance in the convex set for a particular n to the true solution. Now, why would you do that? Well, you will have to do that if this is, of course, not your exact solution. You can prove the analog convergence result. But then what you can do is you can chain those together by, if you have changing constants, changing Lipschitz constants and stability constant with frequency, you can come up with a condition that all those iterations between growing convex sets actually converge back to the solution. This is, of course, what people have observed for years, that if I start with very low frequencies and increase the frequency gradually, I can get surprisingly good examples to work. And this is essentially where that is hidden. So I'll give a few slides how this works. So this is really how you do that. You do not use the pure point of view. The linear case of this whole idea was worked out by Daubechy, Fournagier, and Loris in 2008, and we have here a nonlinear version of that. It's essentially a nonlinear steepest descent with elements of nonlinear conjugate gradient. So Z, this is a space of piecewise constant function, is a closed convex subset. We introduce projectors, can prove that they're always totally non-expensive, a technicality you need. And here's your conditional Lipschitz stability condition from before. That's what we have on this particular set with particular constants. And so now we want to get as close as we can, that is the minimum Bregman distance, or minimum norm in this case, eta, to the true solution. And so you can do the same thing and converge and get exactly to that point. Now I want to do it slightly more general. Since you do approximation theory, you can actually throw in inaccuracy, in some sense statistics, by saying, well, but I can only do that within a delta accuracy. So you immediately for free get a technique to deal with inaccuracies. And then the story is the iteration with projections, essentially the previous iteration with projections. What you should do is you should stop. So you have a stopping criterion, but the stopping criterion is determined by the eta and by the delta. This is the discrepancy measure. And so precisely up to this index, you will reach the point, the optimal point Z dagger. And you know exactly which distance it is, because it is eta plus delta. So that is how those ideas work. And so essentially it's the same equation that I wrote before, a little bit more technical. So the algorithm works like an iteration as before, computing a residual R, computing a dual T, computing the norms. The norms play a role in how the residuals decrease, how this converges. What you see, the important thing to note is that in those convergence rates, in those constants Ck that play a role, you get an accumulation of the previous residuals. So it is a steepest descent, but it's a nonlinear one. In the classical steepest descent, you wouldn't see the history of the residuals. In this proof, you do get the history of residuals, so it has a flavor of a higher order conjugate gradient technique. But mathematically, it's actually equivalent to a nonlinear steepest descent. So essentially, you can iterate out. You see all those constants reappearing as before. Here you see the constant appearing in the stopping criterion. And well, essentially, this is your duality calculation. You do the iteration from the residual, the update, then back to the original and the projection into this convex set. And so where do you stop? Precisely when the residual satisfies this condition, and it happens precisely at the k function that I described before. So you have a complete control in terms of constants, what is actually happening here. And so that brings me to my final slide. And so how do you play the game? Well, by the way, that is the convergence statement of the residuals that I forgot to mention. And here's that statement that you have to stop at k to get precisely this Z dagger. So how do you do this? Well, what you do is you have a nesting, a scaling if you wish, of those convex sets n. And how do you choose them? Well, you choose them in concert with the frequency. So the constants, the Cf and the L hat, will change with frequency of the problem. So let it be a sequence of frequencies omega n that you have chosen. Estimate the constants. The constants will determine then what the radius of convergence is to do the approximate projected iteration, and that this goes in concert with choosing the right number of domains, the dimensions of the domains. So you do a successive, if you wish, a progressive compression of the problem. The question is, can you come up with a condition on the constants that if you go from omega 1 to omega 2 to omega 3, that you get actually convergence as we had before? You can work that out. This is the relation of the constants you get. So you get an inequality where the product of the Lipschitz stability constant and the Lipschitz continuity constants for the successive n's, for n to n plus 1 in a root and in a ratio, should be estimated in terms of the constants of the spaces. So if that condition is satisfied, then you get exactly the same convergence as we had before by essentially doing frequency continuation. And so that brings me to the end of the story. By the way, I should mention there is work, not in the Helmholtz case, by those authors, Jakob Albers and Boutnariou in 1997. There are close connections to multi-grid techniques. I didn't mention that. If you want to look into the details of the proofs, multi-grid is sort of a technique that can be translated into this problem that plays a role in coming up with those sort of estimates for convergence. And this is where I would like to leave it. Happy to take questions.
Questions for Maarten? Yeah, this is very interesting, and of course this is a critical point to be addressed in the development of FWI. But clearly I missed a turn and went off a cliff at some point, because in all of the work, depending on convexity and smoothness of norms, we are dealing with LP, let's say, with P less than infinity, to take the usual examples that turn up. And yet, for the map from C to Dirichlet to Neumann map, that mapping is not differentiable in any of those metrics. Indeed, it cannot be, because there are directions which are not in L infinity. How do you get around that? I can imagine interposing a little bit of smoothing or something like that to take care of the bounds. Yes. But otherwise, I don't see how this applies to this mapping.
You do this conditionally, so you don't do this in L infinity. So it works in a few steps. So you know the condition that you need in iteration.
Yes, but you do have you've quoted some results which really depend on some form of differentiability.
Right.
Here, the most you have is Gateau in a dense set of directions. That's
right.
all.
Yes, but that is all you need to prove this result.
That's all you need.
That's all you need. Yes, that's correct. We actually prove it via Gateau derivatives. I didn't want to go into all the techniques. That's all you need. But the problem that you mentioned is correct. Like, you would like to measure this all in L infinity, and you can't. And so the story is that we have to work our way out of L infinity. For example, the convergence. We cannot really, implicitly you can say, well, all the norms are equivalent. I work with piecewise constant functions. I can use any norm I wish that is equivalent. But we cannot technically do this in L infinity. And that is, I think, the key problem here that is still a very technical challenge, how to address that. That is the issue. But the Gateau derivatives are sufficient for the proof of this. If you don't,
Any other quick questions? Oh, that's like speaker again.